Okay, everyone, we're going to jump right into this. This is Unit 12, Lesson 6, Compound Probabilities. And what we're trying to find out is both things are going to happen. There's going to be more than one thing. Maybe there are going to be 3 things, 5 things, 7 things. Previously, we've been dealing with one event happening, and some of the times mixing in 2 events that are happening. That's a single stage, 1 event, and then multi-stage, 2, 3, 4, 5 things. So given the probability of event B occurring, if an event has occurred, and that's how we write it, answer the following questions. Rewrite this formula solving for probability of A and B. Okay, we're solving for this. How do I get rid of division? I multiply. So the probability that B happens, given that A happens, times the probability that A has happened equals the probability of A and B. This is the big thing right here. How could we write this formula if event A and B were independent? Well, remember from previous lessons, if they're independent of each other, this here, the probability of B, given that A occurred, just equals the probability of B. So we know for the fact that the probability that B, given that A occurs, equals the probability of B. So using substitution, we know that it's the probability of B times the probability of A equals the probability of A and, I ran out of room, so I had to use the abbreviation for and, A and B. Okay, so let's just rewrite this. I'm just going to put the probability of A times the probability of B equals the probability of A and B. What does this mean? This means that you just multiply the individual probabilities. Wow, that's easy. So here, if we have multi-stage experiments that are connected by an and, that just means multiply again and again. Consider the spinner shown below. The spinner is spun twice. The results are recorded. Are the outcomes of the 2 spins dependent or independent? They're independent of each other. Okay. How can we explain that? Uh, you know, we can do it mathematically, but then how do we know if they're mathematically independent? Because we know that they're physically independent of each other. So it's kind of like going in a logical circle. So the question is asking, what's the probability you'll get an even number on the first spin and a number greater than 5 on the second spin? So the probability that's even is 4 out of 8. 1, 2, 3, 4 out of 8. And then greater than 5, 1, 2, 3 out of 8. Probability x is greater than 5 is 3 out of 8. Since this is an and statement, 4 out of 8 times 3 out of 8 is 12 out of 64. Again, I told you I don't like simplifying the fractions. A lot of people simplify them. I don't, because I like to see the sample space. Let's probably spin a prime number and a perfect square in either order. That's a little interesting. In the last video, I told you that we have to answer the question that's being asked. We can't change the question. So this is asking us in either order. So the first question specified that we have to get an even on the first spin and we have to get a number greater than 5 on the second spin. So this one, what's probably going to spin a prime number and a perfect square. So the probability of a prime equals 4 out of 8. They're 2, 3, 5, and 7. The probability that we get a perfect square. The perfect squares are 1 and 4. So that's 2 out of 8. Now, it says in either order. So that means we can have the probability of it being prime times the probability of it being a square. Now, we can get it this way, or we can get it another way. I hope you're hearing this. Or we can get another way. Because this is an or we can get another way. We can get it as a perfect square times the probability of it being prime. That or means add. So we have 4 over 8 times 2 over 8 plus 2 over 8 times 4 over 8 equals 8 over 64 plus 8 over 64, which is 16 out of 64. Remember, if you have any questions, ask. Let's take a look at the next page. The first question on the next page says, as experiments grow more complicated with more stages, theoretical probability becomes increasingly more complicated. Sorry about that cough. It's especially important to note whether you're sampling with or without replacement. Okay, now counting. Counting is the difficult part. Here we have a class that consists of 12 girls and 8 boys. Well, that's not the counting that I'm talking about. It's as the experiment goes on, you continue to count how many people are left. A group of 3 is picked to give a speech. If the students are picked at random, what's the probability they're all going to be boys? Okay, now, first of all, I'm going to tell you the wrong way. I'm going to tell you the wrong way to do this. So don't write this down. Okay, it's not the fact there are 20 people and 8 of them are boys, and then we pick again, and then we pick again. Okay, what's happening here, even though it doesn't say in the question, it says each person only gives one speech. That's why this is wrong. This is wrong. Okay, it's not that. Okay, so let's try to find the correct way. The correct way to do this. Probability event 1. Event 1, first picked as a boy. Okay, again, there are 20 people. And 8 of them are boys. That's event number 1. Now, how many people are left? There are only 19 people left, and 7 of them are boys. That's event 2. And then, how many boys are left? There are only 6 boys left, and there are only 18 people left. So that's event 3. So, we do 8 over 20 times 7 over 19 times 6 out of 18. Notice that these don't say, given. This is just a single probability. We're multiplying the events together. So we multiply those together. The probability that 3 boys are picked is 336 out of 6840. Some of the times it's nice to understand this as a percentage, and it's approximately 5% of the time will only and exactly 3 boys be called on. Next question. In exercise 4, they're talking about safety decisions when you're making something. Okay, when you're designing something as an engineer, you can use these same principles. I use these same principles in determining the probability that you will get the same gender of a fish. if you pick out 8 fish, what's the probability that the gender will all be females? Because obviously when I'm selling fish, people want to have a mixture of males and females so that they can have baby fish. So we can use the same probability for that to make it so small that it's almost 100% that you're going to get both genders. Can't always be 100%, but you can almost get to 100%. So let's focus on question number 4 now. Say that a power generating facility has 3 primary safety switches. 1, 2, 3. In case of an emergency, the probability that any one of these switches would fail is 5%. 5 out of 100, or 1 out of 20. 5 out of 100, and 5 out of 100. What's the probability that all 3 will fail? So is this and, maybe, or? This is multiplying, that's adding. Probability all 3 will fail is an and statement. The first one has to fail, and the second one has to fail, and the third one has to fail. Remember, they're independent of each other. So 125 over a million. So you can understand this number a little bit more. There it is as a percentage. Not less than 1%, less than a tenth of it's well, a hair over a tenth of a percent. A hundredth of a percent, sorry. It's less than a tenth of a percent. That's 1%. That's a tenth. That's a hundredth. Very, very small probability. Last question here. When we're reading this question, I want you to think about, is one event happening or are 2 events happening? Is one event happening or 2 events happening? A company was determining the effectiveness of warranty sales on a computer. They took data on the number of customers who purchased warranties on 2 different brands of computers. If a customer was chosen at random, what's the probability they did not purchase a warranty? Is one thing happening or 2 things happening? Is one thing or 2? Guess what? Only one thing. Is happening. Only one thing is happening here. Wait a minute. We're getting 2 different brands of computers. Yes, but the person is only purchasing one computer, either type 1 or type 2. There aren't 2 things that are happening here. Okay? So, there are 2 ways to tackle this problem. First, let's understand one thing is happening. Secondly, let's understand that 100% of the people bought a computer. That means we only have type 1 and type 2. There's no other type of computer for sale. This does not add up to 100%, and we wouldn't expect it to. When we add these up, it's 91%. So we know everyone did not purchase a computer, a warranty. In fact, of those who purchased a computer, only 35% of those purchased a warranty, and only 56% of those purchased a warranty. So it's not even close. If you look at that, it's going to seem like not even close to 91%. Probably less than half purchased a warranty. That's just a guess. There's only one event happening. So let's figure out the probability that type 1 I just wrote that down wrong for a second. Let's figure out the probability that if you bought type 1, that you have a warranty. Okay. Now, remember something very important here, that I'm grabbing a person at random. A person at random. So what's the probability that person at random purchased type 1, given that they purchased type 1, that they have a warranty? Now, do I want to know if they purchased a warranty or if they didn't purchase a warranty? If you remember several lessons ago, I said that's the not. So given that they bought type 1, what's the probability they did not buy a warranty? Well, if yes is 35%, no has to equal 65%. Now we want to multiply this by the probability that they bought type 1. Here, this really should be the word and, not given that. That really should be the word and. So the probability that they did not get a warranty times the probability that they bought the first computer is 0.65 times 0.35. Sorry, 0.68. I'm just going over trying to look at the table. Let me hit pause. Now, this is an or what about the probability that they did not get a warranty times the probability of type 2? So that's plus not warranty, 56% is yes, so 44% is no, so that's 0.44 times 0.32. Type that into our calculator, and our calculator tells us it is right around 58%. So let's summarize this. I found out what the not was. And then I multiplied it by the 32%, multiplied it by the 68%, and added them together. If you have any questions, make sure you ask me in class. And of course, the probability equals 1 that the next 2 pages are homework tonight, not next week, tonight. Thank you. See you later.